Good afternoon. Let's go ahead and begin. It's a real honor.
Should we like standing there?
Okay, sure. Introduce Dr. Jim Carlson, who I have known far longer than I've known anybody else in this room, since he was one of my professors my first term in graduate school at the University of Utah 45 years ago.
Amazing, yes.
We're still going. So without further ado, he is the former chair. He was the head of the Clay Institute. Maybe you could talk in telling you a little about the millennial problems over the next couple of days, if you're interested. And he'll give a great talk. Jim?
Thanks, Steve. So it's really a pleasure to be here at this event, and I must say I have some very hard acts to follow, so I'll do my best. So I'm going to begin with a somewhat familiar picture. Let's see if I can operate this. So when Mina told me about this, I figured I needed to actually learn some new things about braids. In particular, how do you actually braid hair? Because, you know, that's sort of the starting point. If you can't describe how to make a three-strand braid, what can you do? So there is a three-strand braid. And as Mina mentioned, we both live in Harlem now. And actually, we live 6.5 minutes apart. But in any case, there are lots of braiding studios up there, and there are lots of YouTube videos that describe how to braid hair. So I looked at one of those and learned how to do it. So let's go to the next slide, and I'll give a schematic representation of how one braids hair. So in some other notes that I've got on the internet, I'll talk about those later, there's a little video that describes this. But basically, you start with 3 strands that are just hanging straight down. You take the right one and you cross it over the next one. You can cross it all the way over. No, sorry, you cross it to the middle. Then you take the one that's on the left and you cross it over. And then you repeat that process, right, left, right, left. And so I colored the braid so you can kind of see what's going on. And you see that if you do this, if you do a total of 6 moves, then if you follow a colored strand, it comes back down to the place where it started. So if you think of these as 1, 2, and 3, you start off at 1, you go all the way down, and you end up at 1 again. Okay? And that's kind of nice because if you think of this as sort of a basic braid, you can stack them up. And you know, it's hard to learn how to do this the first time, but then you just repeat that, and you can make arbitrarily long braids of this kind. So that's sort of, we go from, you know, learning how to braid hair to learning how to braid sort of abstract representations of them. And that's really the beginning of the mathematical subject. So let's think now about composition of braids. So Nancy described this, but there'll be a little bit of repetition, but sometimes that's good. So at the top, I've written the braids horizontally this time. So I'm going to call this braid sigma 1. It's a 3-strand braid, just like the hair. And let's see, what do? We cross the number 1 strand under the number 2 strand, and the number 2 strand over the number 1 strand, and the number 3 strand just goes straight across. Okay? We'll call that sigma 1. Sigma 2 is going to be the same thing, except that the 2 strands that we twist are the 2nd and the 3rd strand. And these are going to be the generators of what will become, when we get there, the 3-strand braid group. Now, once again, you can stack these together. And when you stack sigma 1 against sigma 2, you find a new braid where, in this case, the number 1 strand moves over and ends up at 3. The number, whoops, yeah, that's right, it ends up at 3. The number 2 strand moves up to 1, and the number 3 strand moves up to 2. Okay? So, so if you think about this, so let's look at one more. Let's look at sigma 1 followed by sigma 2. And if you look at that carefully, what that really is a double twist of the first 2 strands. Sigma 1 is like a half twist. You do it again, you get a double twist. Okay? Now, another thing you can do is you can take your basic braid, sigma 1, which is a twist in a certain direction. You can instead twist in the opposite direction. So you see here we take the number 1 strand and we go under. Here we take the number 1 strand and we go over. And if we put these two together, we get something that if we stare at it, if we just sort of pull things out straight, just think of imagine that these are made of slightly elastic string, because the bottom string is going to have to be stretched. We stretch it out, and what is on the left, whoops, my computer went to sleep, so this is not good. I'll have to touch it from time to time or it'll forget about us. Okay, so if we stretch things out, then we get this braid, which we're going to call the identity braid. And, you know, as a sneak preview, that's going to be the identity element in whatever the braid group is going to be. So we have these little equations here. Sigma 1 times the inverse of that braid is the identity braid. And I won't draw the pictures here, but you should think about this. If you put braids together, it doesn't matter whether you put the first two braids together and then you tack on the third, or whether you put the second and third braids together and then you tack one onto the beginning of that. So this is something very familiar to us. This is the associative law for, imagine those are numbers. That would be the associative law for multiplication. And it's going to be the associative law for multiplication of braids once we have our braid group. Okay, so I guess I have to talk quickly because otherwise my computer will go to sleep here. So an important thing that we have to think about is when are two braids equal? So I claim that this braid is equal to that braid, and that's this straightening or pulling operation. Okay? Maybe when Rick talks about the fundamental group, he'll give a more formal description of that sort of stuff. Of course, things can get quite complicated. This braid is also the identity braid, and you know, if you pull that out, you will be able to reduce it to this. But a very general and important question, which Nancy mentioned, is how do we know when a braid really is equivalent to the identity braid? When can we really pull and stretch to make it look like the simplest possible thing like that? And one answer to this is use some group theory. So we want to try to codify things using the notions of groups. And you know, it may be repetitious or boring, but it may be useful. I'm going to give a short course on group theory here. So some of us have seen all of this, and for some of it it's kind of new. So a group is a set together with a binary operation. We'll call it circle for now. Question? Yes? Question?
Just like in the previous one, the third one actually wasn't the identity because the second was the third.
I'm sorry, say it again?
In the previous case,
yes.
I'm just being picky, I guess, the third one isn't. Yeah,
Let's see, let's go back to this one. Maybe I didn't draw my picture very well. Yeah. So I was trying to draw them so that they were all on different planes, but I messed up. Thank you. This is good. Now I should say, oh yes, I put it there to make sure that you guys were awake, but actually I made a mistake. Thank you. So a group is it's going to be a set together with a binary operation or a composition law. Now, I always like to think about the etymology of things. So composition comes from the Latin word componere, which means con is together or with, and ponere is to put. So you put things together to make something new. Okay, so that binary operation in more formal terms is a function from G cross G to G. Given a pair of elements, you get a new element, which we call A circle B. And groups are, in one way, very simple structures because they have very few axioms that they have to satisfy. The composition law is associative, just like what I claimed for braids a moment ago. And moreover, there's a special element called the neutral element that when you multiply this element times G, or you multiply G times that element, you get the element back again. So it's acting like 1 when you multiply numbers, or like 0 when you add numbers. Okay? So they have this neutral element, which sometimes we call 0, sometimes we call unit, sometimes we call identity. Okay? And then the third and last thing is that for every element of the group, there's a companion element, G prime, such that when you multiply them together in either order, oops, another mistake. That should be E. I'll correct these when I redo my slides, okay? So G times G prime or G prime times G is not that, but E, okay? So just like with numbers, you know, 2 has a companion element 1/2, so when you multiply them together, you get 1. Or 3 has a companion element -3 in the additive group of integers. You add them together, you get 0. Excuse me. A couple examples of groups. The integers, which I just mentioned, our most familiar group. The integers mod 2. Now, you can think of it in a very down-to-earth fashion. It's just the set 0, 1 with an operation plus that can be described by a table. There's the table. And you also have to be able, for every G, to give its, in this case, additive inverse, which we're going to write as minus G. So the additive inverse of 0 is going to be 0. The additive inverse of 1 is going to be 1. And we just need to check that this is true. Is 0 plus 0 the neutral element 0? Sure it is. That's what the addition table says. Is 1 plus 1 equal to 0? Yes, it is. So just, you know, doesn't take any sophisticated mathematics to see that this satisfies the axioms. You can do the same thing with Z mod 3, Z mod 4, etc. It gets pretty tiresome when the numbers get larger. But you write down the table, and it's easy to write these things down because the first row has got to be 0, 1, 2, and the first column also has to be 0, 1, 2. And then you can figure out what the rest of it is pretty easily. And you can also write down the table of G, excuse me, and minus G. So, you know, 0 plus 0 is 0. What is the inverse of 1? Well, maybe it's 0. No, it's not, because 1 plus 0 is 0. Maybe it's 1. 1 plus 1 in this system is 2, so it's not 1. So it has to be 2. Okay, so it's easy to fill these tables in. So that's sort of the low-down, bare metal approach to group theory. And these groups are very special. They're what are called abelian groups, because if you multiply A times B, it's the same as multiplying B times A. A circle B is B circle A for all A and B. Okay, so those are some little groups. Now let's look at something more interesting and that will be directly related to braids. These are permutation groups. So we'll just again begin with simple examples. What's a permutation of the letters 1, 2, 3? Well, it's those same letters written in a different order. So again, I can describe that by a little table. So there's a permutation, I'll call it pi 1, not to be confused with the pi 1 that Rick is going to talk about, by the way. So what does it do in words? It just flips the first 2 elements and leaves the 3rd element unchanged. And pi 2 is like pi 1, but it flips the last 2 elements and leaves the first one unchanged. And of course, you can think of these as functions. Pi 1 of 1 is 2, pi 1 of 2 is 1, pi 1 of 3 is 3. Okay? And then you can ask, well, how do you multiply permutations? Well, the right answer is you multiply them by composing functions. So here we viewed a permutation as a function. Here we're going to compose functions. And if you do that, you can easily write down the multiplication table for pi 2, pi 1. We'll just do one computation. What is pi 2 of pi 1 of 1? Well, pi 1 of 1 is 2, and pi 2 of 2 is 3. So 1 goes to 3 under this permutation. Okay, so another very simple group. It's a 3-element group. Then the question is, how is this related to braid groups? Okay, well, actually, I guess I want to say a few more things about it. So in general, Pn is going to be the permutation group on n letters, 1, 2, 3, 4, 5 to n. And if we have a pair of permutations, we know how to compose them. And it's also easy to see that every permutation has an inverse. And I'll describe a table theoretic way to do that. We take the table for one permutation, we flip it over, and then we sort it so the first row is all in order, and then the second row is whatever it has to be. And that gives you the inverse, which curiously enough in this case is the same as pi 1. But of course you knew that before, because if you apply pi 1 to 1, you get 2, and you apply it again, you get 1 back again. So if you compose these, you get the identity permutation, which is the one with this very simple table. And notice that this flip, switching the first two letters, has a very nice property. If you apply it twice, you get the identity. So, so now we take just one last look at the permutation group on three letters, and then we get back to braids. So if you write down the tables for pi 2, pi 1, and pi 1, pi 2, you see that they're different. So one thing you see immediately is that this is a non-abelian group. Okay? Pi 1, pi 2 is different from pi 1. Pi 2, pi 1 is different from pi 1, pi 2. And there's also a nice way of thinking about it, because if you write the letters 1, 2, 3 in a circle, then this transform, let's see which one it is. Pi 2, pi 1, it sends 1 to 3. So it's this one, 1 goes to 3, 3 goes to 2, and 2 goes back to 1. So this little circular diagram here gives the same information as this table does. So pi 2, pi 1 is a transformation R, which is counterclockwise, clockwise rotation by 120 degrees. The other transformation, pi 1, pi 2, is the opposite rotation, rotation by 120 degrees counterclockwise. My arrow should be pointing the other way. So if you with that interpretation, it's obvious that if you apply R3 twice, or 3 times rather, you get the identity. So it's what's called a transformation of order 3. That's the smallest number n, such that R to the n is 1. Okay, so we have one interesting permutation group in hand, P3. If you think about it, it has 6 elements, because there are 6 ways you can permute the numbers 1, 2, 3. It's non-abelian, and we showed that it has elements of order 2 and order 3, and those are the only kind of elements it has. There's no element of order 6. That's a nice thing to think about, by the way, so that's a little homework exercise, if you like. Now, what about the relationship between braids and permutations? Well, I claim that there's a nice map that goes from the in-strand braid group to the permutation group on in letters. And actually, if you turn this diagram on its, rotate it 90 degrees so that it's sort of pointing down, and you can think of this red dot as traveling downwards under the force of gravity. Or maybe there's a wind and it's being blown across from left to right. And you see that if I start with a little red dot at 1, I follow its strand, it goes over to 2. If I take that red dot, put it there, it goes over to 1. So this idea of following the dots, or letting the beads slide along the wires, describes a permutation, we'll call it pi 1 in this case, that is associated to the braid sigma 1. And in this way, yes? Yes, absolutely. Yeah. So, for example, we could switch number 1 and number 3, and you could draw the picture to that. That's a nice drawing exercise. Yeah. So, in another thing, another question you might ask is, so let's call them flips. How many flips are there? Well, I guess there are 3, because I can flip 1 and 2, or 2 and 3, or 1 and 3. There are these rotations, and I can either rotate by 120 degrees counterclockwise or clockwise. So there are 2 of those. And then there's the identity transformation. So this 6-element group has 6 elements, 1 of order 1, that's the identity element, 3 of order 2, the flips, and 2 of order 3, the rotations. Okay, so now this relates to what Nancy talked about in the last hour. This map that associates to a braid a permutation is actually a homomorphism. So it's not just any old map. It's a map that's compatible with the group structure on braids on the one hand and the group structure on permutations on the other. Namely, the permutation associated to A circle B is pi of A circle pi of B. So the fact that it's compatible with composition of braids or composition of permutations allows you to do many interesting things. In particular, it's going to allow us to say that certain braids are non-trivial, or that the braid group in general is a non-trivial group. So let's take a look at another relationship with Nancy's talk. So I gave you a homomorphism from the braid group to the permutation group. Okay, braids on in strands to permutations on in letters. Nancy talked about homomorphism of the braid group to matrix groups, maybe ordinary matrices, or maybe these sort of amped up matrices that have coefficients in Laurent series, or polynomials in T and T inverse. Well, there's a relationship between the two, because you see, if I have a permutation, I claim that I can associate to it a matrix. And let's think about that. To know a matrix is to know how it acts on basis vectors, right? And so there's a very simple rule, which is the following. The matrix associated to permutation pi, acting on the basis vector E sub I, is just the basis vector E sub pi of I. So we just permute the subscript, so to speak. And if we look at an example, then the permutation pi 1 has this matrix down here, because you see, what does it do? It sends E1 to E2 and E2 to E1, which means that the first two columns of the matrix are the E1 and E2 columns permuted, and then the third column is unchanged. And the same reasoning tells you that the matrix associated to the second permutation is the one that flips the last two columns. Okay, you can think of all of these things in terms of row and column operations, if you like. Okay, so here's another little fact. Let's see what the time is. I guess, yeah, I guess I can give details. So a really useful fact is that if you have a homomorphism from one group to another, it sends the identity of the group G to the identity of the group H. Okay? So this is one of the first exercises you prove in a course on group theory. So I apologize to all of you who've already taken such a course, but here we go. Let's write down this obvious fact. We'll write down the basic property. What does it mean for E sub G to be the neutral element of the group G? Well, it means that, in particular, E times EG times EG is EG. Okay, we want to relate that somehow to the group H. So what do? We apply the homomorphism to that equation in G, and we get an equation of elements in H. Okay, but by the homomorphism property, this quantity on the left, pi of EG times EG, is pi of EG times pi of EG. So here we use the homomorphism property. And now we have to do one more thing to get home, which is I'm going to multiply this equation of elements in H on the right by the element pi of G inverse. So pi of EG is an element of the group H, so it has an inverse. So we're going to multiply both sides of the equation on the right by that element. And we know that this thing here is going to be the identity on E on the group H, and this is going to be pi of EG times EH. And by the property of the identity element, this is pi of EG. So lo and behold, we've proved that when we apply pi, the homomorphism pi to EG, we get EH. So, you know, if you've already seen this, it's just incredibly boring and tiresome. If you haven't seen it, maybe it went by too fast. But if you think about it in the quietness of your study, then talking too slow again. Whoops. There we go. Okay. If you think about this of the quietness of your study, you see that you know, it all works out. So, by the way, I find that, you know, now that I'm not teaching very much and I want to learn something new in mathematics, I can't just read this stuff. I've got to write out everything by hand. If it doesn't go into my hand, it doesn't go into my brain. You can't just read mathematics and expect to understand it.
It wasn't like that in the past?
Pardon? Well, Yes, it was like that in the past, but I've rediscovered what the past is like. So yeah, good point, Mina. Okay, so here's the important thing. A corollary of this is that if we've got a homomorphism from G to H, and there's an element of G whose image under the homomorphism is not the identity, then that element can't be the identity either. So let me repeat that, because this is really important. I mean, suppose that pi of G, let's see, what did we say? So up here we say that if we've got a homomorphism, then the identity element of G is mapped to the identity element of H. So a corollary of that is that if we take an element of G and we map it to H and it's not the identity element, then G can't be the identity element either. Okay? And a corollary of this is that, well, just for example, B3, the braid group on 3 strands, is not a trivial group. It's got elements that no matter how you pull and push and tug are not the identity. And why is that? Well, it's because sigma 1, for example, has homomorphic image pi 1. It goes to a permutation that is not the identity permutation. So if it goes to the, if sigma 1 goes under pi to a permutation that's not the identity, then sigma 1 cannot be the identity either. So this is a very simple example of the principle that Nancy was talking about. You can use representations to figure out whether things are non-trivial or not. And in Nancy's case, she used big groups. Okay, I'm using very small groups here. These groups are finite. This one, P3, only has 6 elements in it. So the groups that Nancy was talking about have more ability to detect non-trivial elements. Okay. So let me say a few things in the time remaining about the structure of braid groups. Some things are just things that we can harvest from what we already know, and others are a little bit new. So let's go back a step. Let's look at the braid group on 2 strands. Now, a braid on 2 strands looks either like this or like this. It's either twisting a certain number of times clockwise or counterclockwise. So if we can associate to every braid on 2 strands a so-called twisting number. If we do in right-hand twists, we will associate the positive integer in. If we do in left-hand twists, we'll associate to it the integer minus n. Okay? And so there's a map that sends a braid to a number, namely the twisting number of the braid. And it's very easy to see just by drawing pictures that this also is a homomorphism. Okay? That the twisting number of braid B times braid B prime is the sum of the 2 twisting numbers. Okay? So we have a homomorphism from the braid group on 2 strands to the integers, and that's actually what's called an isomorphism. It's a homomorphism that is a 1-to-1 correspondence between the 2 sets. Okay? So that's one fact. The braid group on 2 strands is an infinite cyclic group. Let's talk about B4, and our discussion of B4 will be really a general discussion about Bn. So the generators of B4 are these little flips, sigma 1, sigma 2. Well, I used the sigma 3 that I used is this one here. And this is a good exercise to see that these equations in the braid group are true. These are the so-called braid relations. Okay, so if I stack sigma 1, sigma 2, and sigma 1 end to end, I get the same thing as stacking sigma 2, sigma 1, sigma 2. And then there's a sort of a companion, well, and then there's a similar relation for 2 and 3. So you have this so-called braid relation for braids sigma I and sigma I plus 1, sort of adjacent twists, so to speak. And then you have another relation, which is if the twists involve completely separate strands, then they commute. So if you look at sigma 1 up there, and you look at sigma 3, sigma 1 involves strands 1 and 2, whereas sigma 3 involves strands 2 and 4. And those are completely sort of independent operations. So it doesn't matter what order you do them in. So one thing we see right away is that B4, well, B4 is definitely a non-abelian group because things that happen in B3 already happen in B4. So for example, sigma 1 times sigma 2 is not equal to sigma 2 times sigma 1. Okay? But sigma 1 times sigma 3 is equal to sigma 3 times sigma 1. It depends on how far apart these sigmas are. Now, we're getting close to the idea of a group presentation. That is to say, there are many ways to describe groups. One of them is to give generators and relations. And what do I mean by that? Very annoying. But it gives me a chance to think, so that's good. So we say that a set of elements are generators of the group if every element of the group can be written as a product of those elements and their inverses. Okay? So for example, the braid group on 4 strands, every braid can be written as a product of the sigma i's and their inverses. So that's what's called a word in the generators. So if you think of the generators and their inverses as our basic stock of letters, then a word is just a sequence of those letters. Okay? So, and then the question is, how do you do computations with these things? Imagine that you've been charged with the task of writing a program to do computations in braid groups. And all you have at your disposal are the generators and the relations. So we'll do something very simple here. Excuse me. And you should try more complex examples of this. But let's take the braid sigma 3, sigma 2, and multiply it by sigma 2 inverse sigma 1. So the first thing we can do is by the associative law, we can regroup these any way we want. So we regroup them this way. Here we see we have sigma 2 inverse. That's one of our basic relations. Okay? So the relations are the braid relations together with the relations satisfied by elements of any group. Okay? So we can reduce that to the identity element. And then using the property of the identity element, we can reduce to sigma 3, sigma 1. And then using this relation, we can put things in the correct lexicographical order. So we're getting close to the idea of a normal form, or a sort of a standard form in which we try to reduce every word. And among other things, we should try to put things in lexicographical order. Okay, so let me give you a slightly more general picture of this. So to put this in context, I want to begin by talking about something called the free group. So this is going to be a group that has in generators and no relations other than the standard ones that every group has to have. So we'll call the generators A1 through AN, and its elements are going to be words in the letters AI and AI inverse. So here's a typical word, A1, A5, A2 inverse, A6. And the only relations are like what we had on the previous page, associativity and the fact that inverses do what inverses are supposed to do. And let's take an example of a bigger word. I won't read it, but this long thing here, A5, A1, A1, blah, blah, blah. And if we look at it and we see, let's try to think, how can we reduce this to a simpler form? Well, one thing we spot here is A5 inverse A5. So that can be reduced to the identity. So we can rewrite this word, if we like, in this form, where A1 squared is really just shorthand for A1, A1. Okay? And where A5 to the minus 2 is really just shorthand for A5 inverse, A5 inverse. Okay, so this is a word in reduced or normal form in this free group. And that's the best you can do. And it's kind of a useful thing because now suppose that you have two elements of the group. They're given by words. You want to know, are they the same element or not? Well, you reduce them. You put them in this normal form. And then if they are actually the same, then those group elements are the same. Another way of saying it is I can get from one element to the other by making little moves that are sanctioned by the relations that we have. So again, it's something that you could write a computer program for. It's something that can be done algorithmically. Okay, so I want to get to something called the word problem. So once we have the notion of free group, we can talk about the notion of a presentation of a group. So that's a group that is given by certain generators, and then certain relations, which will simply be a sequence of words that we declare to be equal to the identity element in the group. So I'm going to take as a particular example, let's say it this way, suppose that I just had this, and I didn't have the second part, no relations. Then I would have the free group on 2 letters. Okay? So its elements would just be arbitrary words in A1, A2, and their inverses. Okay? But I have these extra relations. So if I take a word like this, for example, I can rewrite it as A1 cubed, A2, A1, but then you see A1 squared is 1, so A1 cubed is the same as A1. So the normal form now is actually very, very simple. If you give it a little bit of thought, a general word in this group consists of a sequence x1, x2, etc., where each xi is either A1 or A2, and moreover, each of those elements are distinct. So it's a very, very simple thing. Let me show you some of the words on the next page here. So given this description, it's actually possible to enumerate or list the words in this group. So in computer science, to enumerate something means to describe a way of writing down every element of a set in some order. Okay? So here I've done it for you. There's the identity element, there's A1, there's A2, then there's A1, A2, A2, A1. Let's look now at things of length 3, beginning with A1, where there's the only one of them is A1, A2, A1, right? Because, see, you got A1, now what is the second element going to be? If you put A1, then you would have an A1 squared, and that would reduce to 1, so that's no good. So it has to be A2, and then same argument, this has to be A1, and so on and so forth. Or in even more computer sciencey ways, the lexicographical ordering, the alphabetical ordering of elements in G, can be described by the empty string, and then by finite strings of zeros and ones, where you never have a repeated 0 or a repeated 1. Okay? So that's kind of cool. And so you get the description of the group elements in terms of these special binary expansions. And this group has a well-known name. It's the so-called free product of the group Z mod 2 and Z mod 2. So there's another interesting group in your stock of examples. Now, what's the relationship of this to group theory, or to braids? Well, I want to talk about what are called pure braids. So we have our, by now, familiar homomorphism from the braid group on n strands to the permutation group on n letters. And every homomorphism has something called the kernel, which you saw in Nancy's movie. Okay? The kernel is the set of group elements that get sent to the identity. And a little exercise that you should all do if you've never done it before is to show that that set of elements actually is a group. And the main thing you have to show is that if you have 2 elements in the kernel, say let's call them x and x prime, then x times x prime is also in the kernel. So that's a great little exercise in what it means to be a homomorphism. And a fact, which I won't give an argument for here, is that the kernel of the permutation representation is actually isomorphic to a free group on n-1 letters. So, in the language that mathematicians like, you have this so-called exact sequence. You have the braid group, you have the homomorphism onto the permutation group, and then you have the kernel, which sits inside the braid group, is the free group on n-1 generators. And the interesting thing about the kernel is that it's totally invisible to the permutation representations. In fact, it was defined that way, right? It's the set of things that was associated permutation is the identity element. So one of the things that Nancy talked about was the Borel representation, which is an infinite representation. And that has a much greater ability to detect elements. So, you know, her representation can detect things in my kernel, so to speak. So the last thing I want to talk about is the word problem. And the word problem is the following thing. Let's imagine that we have a group with a presentation. So, for example, we had this free product of Z mod 2 with itself. So the group with generators A1 and A2 and just two relations. A1 squared is 1, A2 squared is 1. Or we have the braid group on n generators, which algebraically is given by generators sigma 1 through sigma n with the relations I described, the braid relation and the fact that braids that are far apart commute. Okay? So now let's consider a general presentation. So we have certain generators, certain words that are declared to be the identity. And then the big problem is, when is a word in the generators the identity? Okay? So we have sort of a partial answer for the free group and for the free product of Z2 with Z2. Namely, we have a normal form. We can reduce that to the normal form, and if it's not the trivial normal form, the element is not the identity. But the general problem is, you know, for any presentation, is there some algorithm that allows you to determine whether an element is the identity or not? And the answer is no. It's an unsolvable problem in the sense that there's no algorithm. There's no general algorithm that will do that. There's no Turing machine that you can write down which is capable of doing this. On the other hand, braid groups are nice because the word problem for braids is solvable. Oops, that's a telephone number that somebody need to call. So that's the end. Is sort of in summary, you know, if we look at braids, they are first of all presented as pictures that come from nature, from braiding hair, from other physical processes that have been talked about. They have an algebraic structure, and we know that that algebraic structure, they're elements of infinite order. The braid group in general is not commutative except for B2. It's not abelian except for B2. And there are ways of determining whether certain elements are non-trivial or not, but all of the methods that I've described so far have a defect, namely they all involve some kind of a representation. And the representation I talked about, which is particularly simple, has a very, very large kernel, a free group on n-1 letters. The representations that Nancy talked about are more powerful in this respect. So, and moreover, this whole business of are things trivial or not is related to this general problem of word problems, some of which are solvable, but in general they are not. So that's it. Thank you.